Okay, why don't we get started here? We'll start with some announcements. Lab 1 is going to be out today. It's due 2 weeks from this Friday, so you have 2.5 weeks essentially to finish it. Okay, so watch out for it. I'm going to put it up on the web page and post it to Moodle right after today's class. Okay, that's the first announcement. Second announcement is makeup class. There is going to be another makeup class this Friday, just so that I can cover the last lecture material that you need for the lab. I didn't want to wait for next week. Since the lab is coming out today, we need to cover a little more material. So all the concepts that you need for the lab have already been covered in class. Okay, so Friday, same time, 9 o'clock, this room, we will have our second makeup class. Okay, so I'm going to send an email about that as well. Okay, so let's just get started here. Okay, so I'm going to continue from last time, but let me first stop and continue the parable I was relating last class. This one is called The Lion and the Fox. It's actually a continuation of the story from last time. Okay, so the story goes as follows. Uh, there's a lion in the forest sitting outside a cave, and a fox comes along, and the fox looks very sad. The lion asks the fox, saying, "Why are you so glum?" And the fox says, "I broke my watch, and it's a really expensive watch, a wristwatch." And then the lion says, "Let me fix it for you." And then the fox says, "How could you possibly do that? Your paws are too large, your nails are long, and you couldn't possibly fix such a fine instrument." And then the lion says, "Let me do it anyway." So he goes inside the cave, comes back a little while later, and the watch is all fixed. Okay. A short while later, a wolf comes along, and the wolf is also looking sad. And then the lion asks the wolf, saying, "What happened?" The wolf says, "My hard drive crashed, so my laptop doesn't work anymore, so I can't get any work done." The lion said, "Let me fix it for you." And the wolf says, "How could you possibly do that? Your paws are too large. This is a fine instrument. The screws are small. You couldn't possibly even open the laptop, let alone fix the disk." And the lion said, "Let me do it anyway." So goes inside the cave, comes back, laptop is all fixed. A short while later, the lion goes in, and inside there are 6 rabbits sitting with fine instruments, fixing all sorts of things. Okay? So the moral of the story is, it doesn't matter what you know, what matters is what your graduate students do. All right, so we'll continue from that point on and continue our discussion. So I have few slides on server design issues that come up from some of the material we've covered so far and some that we haven't. This material is probably useful as background for some of the design decisions you may be making for your lab 1, which I said is going to be out today. Okay? This has to do with server architecture, not as much as what the client has to do. Okay, so I have some set of issues. They're in no particular order. I'm just going to go through all of them. Okay? First design decision, as we had looked at before, is whether the server is single-threaded or multi-threaded. I'm going to come back to that in just a moment. Okay, so hold on to that thought. But let's look at these figures here, which are basically relate to how the server, how the client contacts the server, and how the server is going to process requests. Okay, the first figure here basically relates to how does the client know which endpoint the server is listening on. Okay, so you may have more than one server running on the machine. Servers listen to what are referred to as socket or port numbers. Okay? In order for a client to talk to a server, the client has to first make a connection to the server. Okay, the question is, you need to know which port number the server is listening on. Okay? For standard services like HTTP, okay, you have well-known port numbers. HTTP servers by default listen on port number 80. Okay? So a browser can simply connect to a machine on port 80 and it will talk to the web server. SSH service runs on port 22 and so on. Okay, but if you're writing an arbitrary application, okay, then you have to find some arbitrary port number to listen on. And then the question is, how does the client, which is running on a different machine, know how to contact the server? Okay. So there are two ways to do this. One is you hard code the port number in the client. Okay. So the client, you say this service that our application I'm going to write is going to listen on port 8030 or some, you assign whatever port number is not used. You assign it, and then the client is also going to have that port number hard coded, but this is going to work, but it's going to be less flexible. If you need to change the port number, you will have to change the code and recompile it. If that port number is in use on some machine, you cannot actually use it. Okay, so a different way to do this is to use a registry, which is typically also called a name server. So when the server starts up, it is going to register itself with the name server, which is a directory service. Okay, and say this, I can pick whatever port number it wants and register itself, saying I am server such and I am listening on this port. Okay. So now when the client starts up, the first thing it's going to say is, I don't know which port number to use to contact the server. So it's going to ask the directory service instead, saying, is this server up? And if so, what port number is it listening on? Okay. And then the directory service will say, yes, the server came up, it registered itself. This is the port number. So if you need to contact it, go connect on this port number. Okay, so you're going to essentially use a level of indirection where you use another service called a naming service, where you will register your port numbers and then contact the server. So these are two very common ways by which you can decide how to connect to a server, how a client connects to a server. If you do not have a well-known port number that's well established, which are only there for standard services, you will have to use one of these two techniques. Either statically pick a port number, which may not be always be portable. If someone else has some service running on that port number, that's not going to work. Or you dynamically choose a port number, any unused port, and register the server with a naming service, a directory service, and then the client can ask the directory service. Okay, so these are two techniques. The directory service could also be a file that you just store these port numbers, you add the entries or remove. It could be a process, it doesn't matter. That's what is shown in the first figure here. What is shown in the second figure is, once you have established how a client needs to contact the server, how is the server architecture designed? And I had mentioned some of this previously when I said you have a dispatcher or a master thread if you have multi-threaded server that is listening for requests, and when requests come in, you hand it to any idle thread, a pool of worker thread. You can hand it to any idle thread for service. You can do this regardless of whether you have a multi-threaded server or a multi-process server, where the server is a set of processes. You have a master process and slave processes, and requests are sent to the master process, which is the one that's listening for requests on that port number, and as request comes in, you hand it over to any slave thread or slave processes. Okay? This is how you can achieve concurrency in your server design. Okay? So keep that in mind. Okay, there's one last bit here where the directory services on Unix, okay, they are referred to as RPC port mappers. If you're using RPC, which we'll cover in the next class, remote procedure calls, you have a standard service called a port mapper. You register yourself with the port mapper. Okay. There is often also another service in Unix where the servers are started on demand. You don't have a server running if it has no request. You can simply have a super server that dynamically starts servers as and when needed. Okay, so you basically use something called inetd, which is an internet daemon, which can listen onto a set of ports for different servers. When a request comes in, if the service is not already running, you can start that service on the fly. This is simply for efficiency reasons, so you don't have lots of idling services simply running. If you don't have any FTP or SSH connection, you don't need the SSH daemon to run. When a connection comes in, you can start it on the fly. So that's another way by which you can conserve resources on your machine, not have lots of processes that are not doing anything because there are no incoming requests. So these are all design decisions that you can make: dynamically start server, dynamically choose a port number, use a naming service, and so on. Okay. So that's one set of design issues. Another set of design issues that will actually be very relevant in the lab assignment is whether you will make your server stateful or stateless. Okay. A stateful server keeps track of every client that is talking to it by keeping track of its socket ID or some identifier in its memory. Okay. So you maintain the state of connected clients. You can also maintain active sessions. The session is a connection where there are multiple requests that are going between a client and a server. Okay? This is referred to as a stateful server, where the server actually knows about all the clients that are connected to it or are communicating with, shouldn't say connected, but communicating with it in some shape or form. Okay? Now, another way to design your server is to keep it stateless, where you don't keep track of any client. Client request comes in, you service the request, and the connection is torn down. The client needs to make a new request, it sets up a new connection, sends whatever request it wants, the server processes it, sends it back. Okay? So the server is simply accepting requests, processing them, sending back replies, and not keeping track of what clients are sending it requests. None of that is actually happening in this case. Okay? This is referred to as a stateless design. So you could make your server stateful, or you can make them stateless. You can also have something in between where you have something called soft state, where you can keep state of the client for some period of time and then drop it if the client doesn't send any connections or any new requests to the server. Now, whether to make your server stateful or stateless will have important design implications on how your system is actually going to be built. Okay? If you have requests that are coming in, which is when you just have to process the request and send back a reply and nothing more has to be done at the server, it may be fine to choose a simple design and keep the server stateless. Okay? On the other hand, if this server has to track something on behalf of the client and asynchronously send notifications to client, let's say you want to do push notifications. Okay? Many servers provide push notification services. To enable anything like a push notification, you need to keep track of the clients. Otherwise, you don't know who to push what type of notification. Okay? So for any kind of service that requires you to do push, you actually have to make the server stateful, which is keep track of all the clients. Anytime any information needs to be sent to the client, whether the client asked for it or not, if you have to push, then you will have to make your server stateful. Okay? So, and when you keep the server stateful, you will have to keep track of every client to whom data may need to be pushed, for example. Okay? So we'll come back to more of this when we do the lecture on web services and whatnot, because we will see what happens when you make HTTP server stateful versus stateless, what design decisions can be made, how can you use a stateful server in the context of the web and so on. Okay? But this applies to any class of server, it doesn't have to be just the web. Okay? Once you look at the lab assignment, we'll come back to this, you'll see that there are some aspects of the lab that require you to maintain state of the clients, and there are other aspects where you don't need. Okay, so you will probably end up using some form of stateful servers in the lab. Okay, this is depends on how you design it, but that may be very likely. Okay, so that's another design decision to make. The third one is whether you are going to replicate your server or not, and if you replicate the server, how are requests that are coming in distributed across multiple servers. As from a lab's perspective, the first lab doesn't require any replication. It's going to be a single server. But the second lab will actually make you replicate the server and distribute some of the functionality of the server across multiple machines. Okay? So this is going to be more relevant for subsequent assignments, not the current one, but nevertheless I will say something about it here. So what this figure is showing, here is the server itself is a two-tier server. We talked about multi-tier applications in our previous class. So you have a server that has let's say an application tier and a database tier. What is being shown is both the tiers are replicated. Okay, here this tier has 6 replicas. It's running on 6 servers. The code on this that belongs to the app server, and the database is also replicated, and there are 3 database servers that are all replicas of one another that are servicing queries that are coming in. Right? So the real question is, if you have any system where you have replication and there are lots of users coming and making requests on the server, how do you decide which request gets serviced by which server? Okay. One choice you could make is you ask the user statically saying, if you are a user, you go talk to server 10. You go talk to server 5. You can tell the users, and the users will have to make a decision of which server they connect to. But that's not a good design decision, because a priori you don't know how many users are going to access the server, and you can't tell the users unless they ask you which server to connect to. So what needs to happen is, as user requests come in, you have to decide for each request which of the server to send it to. Is that clear what I just said? Okay. This is often done by what is called a load balancer switch that sits in front of the server. Okay. So the job of the load balancer is, if n requests come in, you distribute those n requests across however many replicas you have. Okay. Any policy could be implemented in the load balancer. You can simply do round robin. Okay. So if the first request comes in, you send it to the first server. Next request comes in, you send it to the second server. Third request comes in, send it to the third server, and so on. So each request you send to another server, and then basically you're going to get a load balancing effect because requests are being split across all of the servers in your system. Okay. This is the job of what is referred to as a dispatcher or a load balancing switch. Okay. So there is some entity that's going to sit and then distribute your requests across all of the replicas. That is one way by which you can implement replicated servers, and you dynamically load balance your requests across a group of servers. Is that clear? Okay. Now there are some subtleties here that you may have to keep track of. So for example, if you have state or active user sessions, you may not be able to do very straightforward load balancing. Okay, let's just give an example. So let's suppose this application is being implemented or is implementing an online store. Okay, and the store sells products, so users can come and put a product into a cart and then check out the cart and pay for it and so on. So there is some state that the server is maintaining for each user. So the state could be what is in their cart, for example. Okay, so if you put a product in the cart, you keep state saying this user has put this product in their cart. That's a state that the server is going to maintain on behalf of the users. Okay. Now let's say when the user first came in, they were assigned to the first replica. Okay, and then they put a product in the cart. So that state is now actually in the first replica here. Okay. If the next time they send a request saying I want to check out, that's a separate request. If that request goes to some other replica here, because the load balancer is blindly doing round robin load balancing, that's going to cause some problems because the new server has no concept of what the user has done until now. The state of the user session and the cart is in the first server, which is where the first request was sent, for example. Okay. So when you have stateful servers which are tracking state for each client, the load balancer has to be more intelligent and figure out when this user came previously, which server did I send that request to, and all subsequent requests of that session have to be sent to the same server because that replica has some state that is tracking for the user. Otherwise, your application won't function if you do pure round robin. Okay? If you are stateless servers, this doesn't matter. You can just do pure load balancing because there is no state being maintained. Any server can service any request. There's no dependency on what the user has done until now. Okay? But if your server is stateful, the server has kept track of what the user has done or has some state that it's tracking, then the load balancer or the dispatcher is going to be more complex. It has to track what has been done previously, what replica was servicing this user, and send all subsequent requests from that user to that server. Other users can be assigned to other servers, but for a particular user, you may have to map it to a server, and the entire session has to be mapped to a server. So if in the future lab assignments you make some decisions on replicating your server and you have a load balancer, you have to keep these issues in mind. If you simply say I'm going to load balance, every request goes to the next server, you may not get the desired effect. Yes, there's a question in the.
Can we not replicate the state to the other servers also?
Okay, so the question is, can you not replicate the state to the other server? Clearly, that's another design decision you could make. Okay? You could say that I also replicate the user state. Anytime I have something in the cart, I send that message to all my servers, say here is what's in the cart. So I have the state of all the users on all machines. Okay? If you design your server that way, then load balancing becomes simpler because there's no dependency of a user and a state. State is completely replicated. But it complicates your user system design because anytime the state is changed, you are broadcasting it to all other servers. So you have to now maintain consistency. Okay, so you could do that, and then you have to deal with the consistency of state across all servers. Okay, so any of these design decisions make sense, but you have to weigh Is it more complicated to replicate the state, or is it simply more easier to map a single user to a single machine and not replicate state? Yeah, because other users get spread onto other machines, but the user is mapped onto a machine. Okay. So these design decisions are going to have important implications on what actually is happening. Okay. There are other things you could do where you can make the presence of the load balancing switch. You don't have to do it in the lab, but in web applications they often do this, where a request comes into the load balancing switch. The load balancing switch does what is called a handoff, which is a redirect. Okay. It simply redirects the request to one of the servers in the pool. Okay. And the response actually comes back from the server, not from the switch. Okay. So the client has connected, the web browser is initially connected to the switch. The switch has handed the connection over to a server saying you go figure this out and process this request. And a reply is now actually coming back directly from the server instead of the server sending the reply to the switch and the switch relays it back to the client. Okay. Because the initial HTTP connection was between the client and the switch, not the client and the server. So this requires you to do additional deal with additional complexity where web browser connects to one entity. In this case, it's the load balancer. Reply is coming back from some other entity that you did not expect. If you send a request to some server, you expect the reply to come back from that server, not some other server. Okay. And it requires you to do some networking, implement some networking mechanisms where this server has to masquerade the IP address of this switch so that from a client's perspective, even though the reply came from the server, it looks like the reply actually came back from the initial switch that you connected to, because that is where you have an active TCP connection. If you get a reply from some other random IP address, you don't know what to do with it. Okay? So in this case, you have a bank of servers that are all masquerading. They have different IP addresses, but when they send replies, they change the IP address to make it look like the switch is the one replying. This reduces the load on the switch. Otherwise, all the replies come through the switch and the switch may become a bottleneck. This is meant for better scalability. Okay. So you may have to actually go and implement additional optimizations in the networking stack just to implement replication seamlessly. We won't go into all of that in the context of the lab or anything like that, but in your real systems, they have to do things like this to improve performance. Any questions on this? Okay, specifically the first part, which may be more relevant. Your question is.
You said that we could broadcast the state of the client throughout all the servers. Couldn't we just save it on the database and then every time the client connects to you, just produce?
Okay, so you are saying why broadcast the state? Why not save it on disk? Okay, you could do that. I mean, you have to ask the question: is this memory state something you keep in RAM, or you have to keep the state on disk? You could certainly persist the state on disk. In which case, if the request comes to some other client, that client has to then, or it comes to another server, that server can go back to that disk state. Assume the disk can be accessed on any machine and pull it from there. It's going to add an overhead. A disk I/O is much more expensive than memory. It's not that it cannot be done. Okay? In fact, sometimes servers will do this, but not because they want to do load balancing. Simply that user puts something in the cart and goes away. Okay? You come back later. If you say, look, you have some items in the cart, would you like to buy it? The user may actually buy it and you make money. So you may actually save state on disk for other reasons, because you can't keep it for a week in memory. For an hour, it's a different matter. So you can persist the state on disk. It adds additional complexity. All of those are design decisions. None of this is not something you would not do. It depends on the scenario. What is the cost? What are you trying to achieve? Okay, so you will have to make the right decisions. Any other questions here? Okay, so that's server clusters. Now the last thing I'm going to talk about is on the architectural aspects, and then we'll move on to other things. So this is going to depend. This slide is going to discuss what are the various architectures you can use to implement your server. Okay, and we have looked at this already. Okay, the first one is a single-threaded process architecture. It's called sequential architecture. Okay, then you can use what is called a concurrent or multi-threaded architecture, and there are a couple of different ways you can implement concurrent architectures. Sequential architecture is very simple. Single process, no threading. Okay? Server is simply listening to a request. Request comes in, process the request. If other requests come in the meantime while you are processing the request, they are queued. Okay, they're just going to sit there. Okay? In fact, you don't even implement the queue. They're simply going to sit on the queue of the socket. And then once you're done processing the request, you accept the next request, you process it. Most straightforward way to implement a server. You're not going to give any concurrency or any parallelism. Okay? Multiple requests come in, only the first request gets serviced, the others are queued and serviced one at a time. Okay? Single process, sequential architecture. Okay? Then you can make the server multi-threaded or multi-process, where there is, as I said, there is a master thread or a master process, and there are some slave threads or slave processes. Okay? So in this case, the master thread or the master process is going to listen for requests, okay, and it's going to assign that request to a particular worker thread or a worker process. Okay? That process is going to process the request and send back a reply. Okay? This is going to give you some form of concurrency or parallelism, because multiple requests come in, you hand them over to multiple threads, okay, or multiple processes, and they can all work on their individual requests in parallel. If you have multiple cores, you will actually get real parallelism. Okay? So requests in this case will not have to wait. Okay? Now this concurrent architecture, there are multiple ways to implement it. The simplest way is what is called a thread per request model. Okay? So in this thread per request model, so you have, let's say, the master thread. Okay? In the thread per request model, you basically create these threads, or it could be a process per request. So you'll have to create processes on the fly as each request comes in. Okay? So when a request comes in, you will create a thread. Okay? And you will hand that request over. Say go process it. The thread will go process the request. When the request is done, the thread will terminate. Okay? So you are dynamically spawning threads or processes. As more requests come in, you will spawn more threads. Okay? So you can scale up as much as you need. Depends on how much concurrency you are seeing in the system. If 10 requests come in, you will create 10 threads on the fly, and each request will be given one. Each thread will be given one request, and you are done. Okay. This very simple model is called a thread per request model. In this case, the worker threads or worker processes haven't been pre-created. You are creating them on the fly as requests are coming in. Is that clear? Okay. So that's the first model. The second model is you basically pre-allocate a pool of workers. Okay. So in this case, when the server starts up, the master thread is started, and then you will create maybe, let's say, a pool of n threads, or if it's a multi-process, you will create n processes. You can pick whatever n you want. Okay, so n will limit the amount of concurrency you can support. If you pick n is 10, that means your server is capable of simultaneously servicing 10 requests. If you make it 12, you are simultaneously capable of servicing 12 requests. Okay? So in this case, the threads are pre-allocated in a worker pool, and as the requests come in, you are going to assign them. Okay? If more than 10 requests come and you have created a pool of 10, first 10 requests will get serviced, okay, and any additional requests have to wait until one of the worker threads becomes idle again. Okay, this is how you are going to manage a static pool of worker threads or worker processes. Is that clear? Okay. Now, it is possible, obviously, for this worker pool to be shrunk or grown. Just because it's static doesn't mean it doesn't change over the lifetime. If you start with 10 threads and you find that there are lots of requests getting queued and not getting service, you can dynamically add maybe 3 more threads. So now you grow to 13. Or if you see that threads are just sitting there idle doing nothing, you can shrink the pool. Okay. So the simplest technique here is to create a static pool. But that pool can be grown or shrunk, which will add some complexity to your server, but you can then scale the capacity or scale it down as you need to. Okay, so the request per thread model is fully dynamic. You do not have to decide how much concurrency you want. You just simply start spawning threads. Each thread will service exactly one request and terminate. In the static pool, the threads live for the entire lifetime of the server, and they will process many requests. Okay, each request that's handed, they'll process, and they'll go back to idle state, waiting for the next request to be handed to them. Okay. And the size of the static worker pool, it doesn't have to be fixed. You can change it based on load and so on. That makes the server design more sophisticated. Okay, this model is actually used in the Apache web server. It's a very popular web server that is used to service any websites or host website. In Apache, you start with the default number of static threads, and Apache monitors the load on the system. As it sees the load is going up, it can dynamically increase the size of its worker pool, okay, to up to some specified max, and then you can keep increasing or decreasing it based on how much concurrency it sees in the system. It's a fairly sophisticated server from that perspective. Okay. So let me ask a question. Why do go to a static pool when you could scale arbitrarily to any concurrency you want with a thread per request model? The thread per request model, when 100 requests come in, you spawn 100 threads. Okay, each is going to service a request and the thread will terminate. Only 5 requests come in, next time only 5 new threads are created. So it seems like a request per thread per request model can gracefully adapt to whatever load the system is seeing. You don't have to predetermine, am I going to see 5 requests at once, 10 requests at once, 100 requests at once. How many requests come in, you spawn that many threads for that time instant. So why would you not actually just use a thread per request model? Why have a static pool at all? Yes, Patrick.
Every time you process a request, you make a system call.
Okay. Every time you process a thread, you make a system call. People agree with what was said? Yes, every time your request comes in, you have to create a thread. Is that good or bad? So you have to ask the question, what is the overhead of creating a thread? If the thread creation overhead is high, then you're doing this for every request. So every request is being taxed by an additional overhead, not only the amount of processing time you need to spend on the request, but the time to create a thread is a tax that you're putting on that request, and it's an additional load on the server. Okay. As it turns out, thread or process creation is not cheap. Okay. If you remember when we said kernel level and user level, if you had user level threads, maybe it's not that expensive because those are all library calls. But most of the threading systems are kernel based. They're a kernel level thread. They require you to make a system call to tell the OS saying start a new thread. Okay, so it's not a cheap operation to spawn a thread. Okay. So if that is the case, then since you're paying this overhead for every single request, you're paying the overhead of creating a new thread. That may be expensive. Okay, so, and you basically are adding additional load on the server for no good reason. So instead of that, if you pre-create a pool, then you pay that overhead only once for the entire lifetime of the server. The server is running for 7 days. When you boot it up, it creates 10 threads. That's the only cost you pay. The threads are there. You don't pay the overhead of creating them over and over and over again. Okay, but the disadvantage, as we saw, is that if you pick n, then you are stuck with that concurrency limit. If more than n simultaneous requests come in, those requests are going to be queued until you decide to spawn additional thread if your system supports that at all. Okay, if you just say static pool, I cannot even change the size of the pool because I wrote a simple server, and you're stuck. If concurrency is greater than n, so request will wait. Okay, then they will have increased latency. Your users will see longer time for the server to reply. Okay, so there are all these trade-offs you have to weigh. Okay, do I pay the price of creating a thread every time? Okay. If you are willing to pay that price, then you don't need to worry about what level of concurrency will my system support. If you feel that the overhead is high for your system, you have to go with a static pool. Okay. If you feel that the concurrency cannot be predetermined, you have to make a dynamic pool, not even static. Okay. So all design decisions to be made when you decide whether to do concurrent stuff. The other dimension is whether you are using multi-threaded or multi-process. Okay. Rather than using multiple threads within the same process, you can also spawn processes and hand them requests. Okay, that's an alternative architecture. Now it turns out creating processes is even more expensive than creating threads. So if you go for a process per request model, every time a request comes in, you're going to start an entire new process just to service that one request, and the process will terminate. That's an even higher cost. Right? So if you have multi-process architecture, often you're going to go with a pre-spawned pool because process creation is even more expensive. Thread, if you have threaded servers, some servers still go with the request per thread model because that is easier to code up and whatnot. But when you have multi-process architectures, you will not do that. You often go with a static pool, okay, or you can change the pool on the fly. Okay. And then there's one more architecture which is called asynchronous architecture. Yeah, that is often used if you have a pure sequential model, where I said you can only service one request at a time. The only way to get any sort of concurrency in a pure request model is to implement your server with what are called as asynchronous non-blocking calls. So what would happen in this case is request comes into your server. It's a single threaded server. Okay, let's say it's a web server, just as an example. Request comes in, the client has requested an HTML page, let's say. A very common type of HTTP request. The way the server will process this request typically is it will go and fetch the file that stores that HTML page. So you'll go read the file and you will send the contents back to the client. Okay, that's how you service a request. If you ask for an JPEG image, the image is typically on disk, you're going to go fetch it from disk and send it back. Okay? So typically request processing will involve some IO. Okay? And IO is blocking. Okay? That means when you are trying to read the file from disk, the server is going to be, process is going to be blocked. Okay? Because you have to wait for the disk IO to finish for the file to be read in before you can reply. Okay? So while this IO is taking place, not only is the server blocked waiting for this request processing to complete, all other requests that have come into the system are also queued up and also blocked. Okay? So one way to actually not have this level of inefficiency is to implement non-blocking IO. So in this case, when a request comes in, say give me this HTML page, you make a file system read, you say read this contents of the file, but you use a non-blocking version of read, which says I'm not going to wait for the read to finish. I'm just going to issue the read to the OS, and the OS will notify me later when the read has finished. So you can continue execution. Okay? So what you would then do is, since this request is still being processed by your file system, you'll go take the next request from the queue and start processing that request, and maybe you'll issue another IO call. Okay? And that was also non-blocking. It's sent off saying go read this other file, and then while that is in progress, you can go process yet more requests. Okay? At some point, some of these IO requests will finish. The OS will signal the server saying your first IO has finished. The server will then have to go and take that contents of that file that have been read in at this point, construct a reply and send it off to the server. Okay? So you will not block on any IOs because you're using non-blocking calls, and you'll get some degree of parallelism as a result. Okay? Not real parallelism, some concurrency, because you can actually, multiple requests are being serviced. You don't wait for the first request to finish before you start the processing of the next request. Is that clear? Yes or no? Okay, so if you look at the timeline, okay, of how the server is processing requests, so let's say this is time. Okay, if you had a pure sequential server with blocking calls, you will basically say this request 1 came in, you processed it. Then request 2 you picked up from the queue, started processing it, request 3, and so on. Okay? And while each request is processed, all requests are queued. Okay? If you use asynchronous calls, what will happen is you will basically take the first request, you start processing it, but since it may need disk IO, you will basically issue a read in a non-blocking fashion while that read is in progress. Okay, so now IO is in progress, you can pick the next request, okay, and start processing it. It will issue another IO, and then they will basically do IO processing. You will do the third request and so on. Okay? So you have overlap of CPU and IO happening in your system, okay, through non-blocking calls. And in this case, you don't wait for each request to finish. You can start processing request 2 even before request 1 has finished, if request 1 is is doing IO, for example. Okay, this is called using asynchronous communication or asynchronous non-blocking IO in single-threaded processes. Okay, is that clear? So we basically talked about 4 different architectures: pure sequential, single-threaded blocking calls, okay? Event-based, which is the name for using single-threaded but using asynchronous calls. There's multi-threaded, there's multi-process. Okay, so you can implement your servers using one of these 4 techniques. Okay, so I just want to take a pause here and see if you have any thoughts on the relative efficiency of those 4 techniques. Okay, which one is going to be the most efficient, which one is going to be the least efficient, and what actually impacts the efficiency of the server. So if you have to process, let's say, 10 requests total, okay, which of the servers will take the least amount of CPU time or the least amount of time, and which one will take the most? Yes. Most will be taken by sequential, okay. So time, and then what about the overhead? There's latency and there is processing overheads. Yes.
Process based would have the most overhead.
Okay, process based will have most overhead, and what do you think will contribute to that overhead?
Creating those 10 processes.
Okay, so creating 10 the processes will cause overhead. What if it was a static pool?
You would still be creating some number of processes beforehand.
Okay, so you'll create the processes beforehand, fine. What happens when after they're created? Is it efficient after that point? Or is it not efficient? So there's a process creation overhead, that we agree. Is there any other overhead once you created the process? If I say ignore the process creation, let's put that as startup. System is booting up, I don't care at that point. After it has started running, what overheads do we care about at that point? Patrick, you had something?
The message passing between processes.
A message passing. In this case, let's say you're just handing a request to a process, there's nothing more to do. So we'll ignore that for now. We haven't even done messaging, so we don't know anything about messaging. We'll come back to that next time. Yes.
Process scheduling.
Okay, process scheduling is an overhead. Okay, request, if you have 2 requests being serviced by 2 processes, you have to context switch between them. So context switch is an overhead you have to think about in this case. Okay, in multi-process, you will be switching between processes. In multi-threaded, you are going to switch between threads. Okay, if your 2 threads are servicing 2 requests, you have to switch back and forth between them. Okay, that's an overhead you will have to pay. Okay, that's an OS overhead of switching between threads and switching between processes. Okay. So in addition to creation startup overheads, which I'm not saying we ignore, there are other overheads to also think about, which is what overheads do you incur when you have multiple requests being processed. In these 2 cases, those are context switch overheads that you are actually going to pay some price on. Okay. And it should be clear that switching between processes is more expensive than switching between threads, because threads belong to the same address space. Context switches are cheaper. Okay. So ignoring the startup overhead, which you do have to consider, but let's ignore that just for this for a moment. If you're actually looking at runtime overheads, process-based will be more expensive in terms of context switch overheads than thread-based. Okay. And both of those will be more expensive than the first 2, because in this case there's only one process. There's nothing to switch. All requests are only being serviced by one process. So let's assume this is the only process on the system. So you don't have to switch to anything else to service multiple requests. You just have to sit within the same process and keep processing requests. Okay? So these 2 architectures are going to actually be more expensive in terms of context switch overheads. They are going to be more expensive. Okay? There is more concurrency there that we should still keep in mind. Okay? So then the question is, pure sequential has no concurrency at all. It's going to be really slow in terms of overall latency. So how can you compare asynchronous IO, event-based versus multi-threaded and multi-processor? Which of them will have better efficiency from our perspective? wants to guess? Yes, Patrick.
I would guess that the context switching is going to have more just from like the versions of Nginx and stuff for higher
Okay.
performance.
So you are saying context switching is going to be more expensive than implementing asynchronous I.
Yeah.
That's what you were saying. Okay. Anyone have anything else to say something? Say something to say?
If we have multiple cores, then we can use those in thread based. But if event based, you'll be just using one core.
Yes. Okay, so those two are actually the right answers. Okay, so the answer is it depends. Okay, there's no one right answer. If you have a single core system, okay, just one core, no processors, event-based architecture is the most efficient of the four. No context switches, and yet you get concurrency because you do non-blocking. You're not waiting for anything. You can service as many requests as you want. You're just only going to be bound by the speed of your disk to service the request. You're not going to wait for one request to finish to do the next one, which is the same thing that happens in threads. You don't wait for the first worker thread to finish before you start the second worker. So you get concurrency in both of those cases. Here there is no context switch overhead. Here there is context switch overhead. So in a single core system, event-based architectures are the most efficient. You cannot do any better in terms of all the taxes and overheads you pay. Okay? But the disadvantage here is as soon as you go to a multi-core system, there's only one process. There's only one thread within that process. So you cannot take advantage of multiple threads at all, multiple cores at all. So in that case, a process-based or thread-based will win because you can get true parallelism. Okay, you can use both the cores and double the processing capacity of your system, for example. Okay, so those are all considerations to keep in mind. Okay, very efficient systems are always written as asynchronous event-based. They're very complex to write. Code is a lot more complicated, but they're really efficient. So if you really need a very high performance server, what you will actually do is have as many processes as your cores, and each process does event-based. Okay, so you will actually use a hybrid architecture where you will create one process per core, and each process is going to service asynchronous I. Okay, those are the most efficient servers you can actually write. They are very complicated. If you want to do somewhat simpler things, you will go with a thread-based or process-based that allows you to take advantage of multiple cores. There's a little bit of tax because of context switch, but that's acceptable because you don't want to write a lot more code to get that extra 10% performance. But if you care about that, you will actually pay that cost. Okay? Any questions here? All right, so we'll continue from this point. So that's all the design decisions to keep in mind. I won't talk about scalability. We talked about that already before. I'll move on to the next topic, which is related still on process and code migration. We mentioned some process migration when I was talking about distributed scheduling, and we talked about the Sprite operating system, where I said if you move a job from one machine to another, if the job is already executing, it's a process, you have to move that process. And I said at that point, we'll come back to this topic and look at it in a little more detail, which is what we are going to do today for the rest of the class. Okay, so I'll talk about how this works and so on. Okay. So when you are trying to migrate any job from one machine to another, and why we migrate, we looked at before, you could just be simply doing distributed scheduling. One machine gets overloaded, it decides to offload some work to another machine, and if there are processes running or new jobs arriving, you just offload those processes or jobs. That requires you to migrate a process or migrate a job from one machine to another. So the question is, what are the OS level mechanisms you are going to need to implement this? Okay. So that's really what we are after, and I'm going to distinguish between what we will call as process migration versus what we'll call as code migration. Okay, so in a process migration, which we'll also call strong mobility, you already have a process that's executing in the OS, and you're taking the entire process and moving it, which means you're taking its memory state, all of whatever it's accessing, and you're moving that to another machine, and the process continues to execute on the second machine. Okay? This is referred to as process migration. Okay? Code migration is something much simpler. Okay? In code migration, think of it as you have the source code, or maybe not source code, maybe binary of the application. You simply move the code and you start a new process on the new system. So you're simply moving code and then you start a new process using that code on the second system. It's much easier to do. And let's say you had a script, a Python script or some such thing. Code migration simply says take that Python script, copy it to the second machine, start the script there. That's code migration. Okay, much simpler to do. You can just do this yourself manually. Instead of running the script on one machine, you move it to another machine and execute it. Or you could move a binary. It doesn't matter what the code is, simply moving the code to a second machine. Okay, this is referred to as weak mobility. Okay. The first case, the code has to move because that's part of the process, but there's process state that's also moving with it, all the memory state. In this case, there's no process hasn't even started. Simply moving the code and you're starting the process on the second machine. In either case, you're taking a job and moving it somewhere, executing it somewhere else. So one is simpler than the other. Yeah, there are many other examples of where you encounter this in practice. Okay, so there are examples that you may have encountered that are some form of code migration. So let's say you are filling a web form in a browser. Okay? In this case, the server has sent an HTML page, but it's embedded some JavaScript in the HTML page just to do validation, for example, to make sure your date is entered in the right format or whatever else it may be validating. Okay? That's a form of code migration. Okay? Some code came to your browser from the server. Your browser actually has a JavaScript engine that is executing the code. Okay? So code migration. Same thing if your Java applets, which are not used anymore, or Flash code, the server is sending you some program that is either written in Flash or in Java as an applet. Your browser downloads it. So the code came from the server to the browser. The code is actually executing in the browser. Okay, that's another form of code migration. Okay. So it's more common than just distributed scheduling is what I'm just trying to point out. Even some simple things like you make a search engine query. Okay, you just go to Google, you type in some keywords and you send it off. That's actually a query that you just sent. Okay, they may be simple text word keywords, but from a search engine's perspective, that's a query saying send me all results that match this query. Okay, so that's a query. Query is a program that has actually been sent off to the server and the server is executing. That's a reverse form of code migration where you send some code. You could have typed a SQL query and sent it off to a database server. Same thing. You send a server SQL query from one machine to another. So all of these are examples of code migration. Okay, the process is instantiated at the other end. Okay. Process migration, we already talked about. Distributed scheduling is the most common use case of why you may need process migration. It's often done for load balancing purposes. There are more processes on one machine that are imposing a heavy load. There is another machine or some other set of machines that are lightly loaded. You move the processes there and you run them there to completion. Okay, so that's an example of process migration. Okay, strong mobility. Okay. There are other use cases for doing code or process migration. Here is an example of what is referred to as driver on demand. Okay. It's an example of code migration. So this is a very straightforward use case. You have some new hardware device. Let's say it's a printer. You simply plug it into your machine. Okay. It's not pre-configured. So there's no driver for it on your machine. Okay. The old way, manually the user has to go fetch the driver and install it. Okay. And only then can you make the piece of hardware work. Okay. Most modern operating systems, what they will do is they have a library of all the drivers somewhere on the internet. Okay. They will actually recognize that this is a printer of this type. They'll go query the library saying, do you have the driver? They'll download the driver on demand because you need a network connectivity for this to happen. They'll download the driver, they'll install it, configure it on the fly, and your printer is ready to go. The user doesn't have to sit and find the printer driver and download it, install it. The OS is doing all of that for you. Okay? So you will have some database of drivers. You connect a device, the download driver is fetched on demand, installed. Okay? Example of code migration. Driver is a piece of code. In this case, it's typically a kernel module that's been downloaded for you. Okay? This makes system configuration easier. Okay? That's another example of where you encounter this type of systems. Okay. Now the question is, how do some of these things work? And I'm going to talk about this at a very high level, and we'll look at some details. Okay. So first, let's try to understand what is involved in implementing process migration versus code migration. In a process migration, the entire process has to move, which means that a process, everything that's associated with the process moves. Typically, that's the code, the binary code that's part of the code segment of the process, any resource segment, the stack, heap, and data segment. Okay, so if you draw a picture here, okay, I had drawn this picture a while back. So if you look at a typical process, okay, that's executing in memory. Okay, this is the memory state of the process. It will have multiple segments. There is a code segment which is also called the text segment in some cases. This is simply the machine instructions that you have written for that process. Okay, this is the binary that's loaded in memory for that process. Okay, you will have the stack. The stack may grow up. You will have the heap segment. So this is all where the variables are stored. That are local variables, global variables, all the data associated with the process. Okay. So if you are going to move the process, everything that's in the memory state of the process has to be copied to the other machine. Okay. So the code segment has to move, all the resource segments have to move, and so on and so forth. So all of that has to move to the second machine. Yeah, and there are other complex things that have to happen, which we'll talk about on the next slide. But at least that has to happen. Okay, your OS has to support this function where it takes the process state and moves it. Now, if you have weak mobility, this is much simpler, as I had already mentioned earlier. You are simply taking the binary program from a disk and copying it over to the new machine, or if it's a script, you're simply taking the script file and copying it to the other machine and just starting it to execute it. So the process is set up after the code moves, you start a new process there. This is much simpler to implement. Okay, you don't have to go and do this complex thing where you're taking the memory state and moving everything over. That's a lot more complicated to do. Just moving some code and you're restarting a process is much more straightforward. In some cases, you may not have to move anything at all. If you have a distributed file system where the files are accessible from multiple machines, there's nothing to move. You simply tell the other machine, go to this file and start executing it. Okay, so there is even less overhead if the file system is actually shared across the machines that are moving code. Okay, but if there's no such file system, you have to actually copy the code. Okay. So here you transfer the program and then start a process from the program. Okay, a simpler thing to do. Okay, the other dimension is who initiates the mobility. Is it initiated by the sender or is it initiated by the receiver? And the answer depends on what scenario you are trying to use it. When we talked about distributed scheduling, we talked about sender initiated and receiver initiated. In one case, the sender was initiating the transfer of, and in another case, the receiver was initiating the transfer. There are many similar use cases. Okay? So you may have, let's say, I give the example of downloading a Java applet or a Flash and so on. Okay, that is initiated by the receiver. This is your web browser. Web browser sends a request saying, give me this HTML page. HTML page may have some JavaScript, it may have a Flash embedded in it, it may have some Java applet. Okay? But it is the receiver. Receiver initiated the transfer. And the source code, not the source code, the code for JavaScript, all of that is at the server, which is the sender. So sender is sending that. But the receiver initiated the transfer by making, in this case, an HTTP request in the browser to the server. Okay. You can also have sender initiated, where the sender is actually sending the code over. Okay. So the simplest example here is you type the search engine example. You type the keywords and you hit submit and you sent off these keywords to Google. Okay, that's a search query. Okay. Query, as I said, any query is a program. Okay, however, it's written as text or not. So you basically sent off a query off to the server. You are the sender. Okay, the search engine in this case, Google, is the receiver. So that's a sender-initiated migration. Okay, so you can have the migration can be initiated by the sender or the receiver, and you can have process migration or code migration. So these are all independent dimensions. Is the code getting transferred or the process? Is the sender initiating it or is the receiver initiating it? Okay. And the last part is who is executing whatever has been transferred. Typically, the new machine is going to execute it, but that raises the question, are you executing code or process? Depends on whether you're using strong or weak mobility. When your code migration, typically, when the code arrives, you will execute it in a new process. Okay? You send off a batch job. The batch job is moved to a new machine. You start a new process for the batch job. And that's not always the case. Okay? In the browser example, the code that has come over to the browser may execute in the context of the browser process itself. You don't even start a new process. Okay? Browser is already running. You you fetch a web form. Web form has JavaScript in it. Okay? The JavaScript is actually executing in the browser process. You don't start a new process to execute that JavaScript. Okay? So in what that means is even in code migration, when some new code arrives, you may not necessarily execute it in a new process. In some cases, you will execute it in the current process that requested it. Okay? So that's an example of code migration where you don't necessarily start a new process. Okay? Now, process migration, when the process moves, obviously it's a new process that has to start up there. Okay? So there are many ways to do this. Okay, we'll talk a little bit about process migration. There's also something called remote cloning, where you make a clone of the process, which is basically a mirror image of the process, and then execute the process on the other end. And both are very similar, so we won't distinguish between them. We'll just talk a little bit about process migration. Any questions here? Okay, so this is just a picture that shows you all of these possibilities, showing you that depending on your system, you may have weak mobility or strong mobility. Within each of these, you can have sender initiated or receiver initiated, and within each of those four, you can create a new process to execute whatever code or data or process is migrated, or you can start execute it in the current process. So you will basically get different endpoints here. Okay, so that's basically each of these paths is going to result in a specific system that has made those decisions. So this one says, I use strong mobility, is receiver initiated, I migrate the process. Or this one is I use weak mobility, it's sender initiated, I'll execute that in a separate process, whatever code came. So we already talked about 3 dimensions. They're all independent. So any combination will give you a particular system that has made certain decisions. Okay. Okay, so now the most important part, okay, all that was more straightforward. The most important or the hardest part to deal with is what happens to resources that your process is actually accessing. Okay? This is where all the complexity of doing process migration or code migration sets in. Okay, process that when it starts up or is executing may need several resources over the lifetime of its execution. Resources could be as simple as files. Okay? You start a process, it's going to read some file and process it. Okay? Let's say you move that process to some other machine. Okay? If that file is not accessible on the other machine, the process cannot continue. Okay? Because it will try to issue an IO request to the file system on that machine. File system will say, I don't even know what this file is, and your process will get an error and stop. Okay? Or you may have a process that is trying to print. On your machine, you have a local printer, so it can print. And if you actually happen to move it to some other machine and there is no printer on that machine, if it tries to do print, nothing will happen. The machine won't work, the process won't work. Okay, so you may have hardware resources. Yeah, printer is just an example. It could be any hardware resource. You may have software resources like files that you are trying to access. When you move a process or move the code, if those resources are somehow not accessible on the second machine, process will not work. Okay? The most complicated is actually network sockets. Okay? If you have this process communicating with other processes, this is where it gets really messy and complicated. If you simply move that process to a second machine, the IP address of the process is itself changed. So this is not going to be seamless to whoever is communicating with the client with that mission, with that process, because you are communicating with the process at its old IP address. Suddenly IP address changed. Okay, so I don't, as the other endpoint, I don't know what to do. Okay, think about this. You have a browser that's talking to a web server. Okay, suddenly the web server has moved to some other IP address. Your web browser was in the midst of sending an HTTP request. It will still go to the old machine because it's going to the IP address of the machine, not to the process. Okay, and now the process is now on some other machine. Client server communication is not going to work anymore. So network sockets are the most complicated resources. They are the hardest to deal with. We won't talk about network sockets today. I'm going to say a little bit about how these other resources can be handled. okay, which are files and printers and whatnot. Okay, so before I even talk about solution, let's ask, or let's not ask, but let's look at what kinds of resources we care about. Okay, so we are going to look at two dimensions of resources. Okay, what is the type of the resource, and how attached is that resource to a particular machine. Okay, so here we have the first category. We have three classes. Okay, you have a resource that you identify using its identifier. This resource could be a specific website, a URL or something like that. You could have a resource that you identify by value, saying I need the C library version 1.1. Okay? Any C library that's 1.1, that C library, any copy of it will work, not that particular one. In this case, if you say I need to talk to that FTP server, you can't say any FTP server will do. You are actually trying to access a particular FTP server. Here, any library with that version number might work for you. Okay? And then the last one is a very loose binding where you say, I need a printer. Okay, I don't care whether it's an HP printer or some other printer. I just need to print something. Okay, there's very loose binding. You just say the resource type is printer, but you don't really care about the exact model of the printer and so on. Okay, so when you talk about resources that a process is trying to access, there is some degree of how strongly you want to bind to a particular type of resource. And as you go from the top one to the bottom, there's a looser binding. Here, you want to access a particular machine or a particular server. Here, you want to access something that has a certain type, but any copy will do. And here, you don't even have that level of binding. Okay, so this will allow us some flexibility in what action we take in order to make a resource in that particular category accessible when the process moves. Yeah. The second dimension here is how easy is it to move a resource should you be willing to do it. Yeah. So you have something called unattached resources where you can freely move it. This could be files. You can move a file when I move some process. Yeah, they are not attached. Yeah. You may have fastened resources. Fastened resources are resources that you can move, but the cost is high. Yeah. Example of it just could be a large file or a large database. So process is accessing a database. Database is 10 gigabytes in size. Okay. Could you move it to another machine if the process moves? Yes. Is it expensive to move? Also yes. So typically you don't want to just move 10 gigabytes of data for no good reason. You better make sure that it's going to take some time to do it and you are paying the price for some benefit you wish to achieve. Okay. So those are called fastened resources. These are resources that can move, but the cost of doing so is high. Last one is fixed resources. These are resources that you cannot move. Okay? Printer is attached to this machine. Of course, you can pick up the printer and move it, but you can't automate it. Okay? You can't write a script that will move the printer. Okay? So that's not going to work. Okay? Network endpoint, same thing. IP address attached to a machine. You can't simply switch an IP address. Okay? So you assume that these things you are going to have to deal with in some different ways. You can't simply move it even if you are willing to pay the price. Okay. So we have different types of resources. Okay. They have different constraints. When a process moves, depending on where it falls, you are going to make different design decisions on how the process can continue to access that resource. Okay. And here is a table that's going to show you what to do or what you could do depending on whether you have a resource that you identify by identifier, value, or type, or whether it is easy to move, it is hard, expensive to move, or it cannot move. So depending on where you fall, you can make one of many decisions in many cases. Okay? So first, let's take the hardest one, okay? Which is this one. These are resources that you cannot move. Okay? Those are the fixed resources. Process is moved. The process was accessing some resource. Resource cannot move with the process. How is the process going to continue to access the resource in this case? Okay, don't look at the slide. Think. So let's make it more concrete. You have a printer attached to this machine. I moved a process that wanted to print to this printer to some other machine. How is the process going to continue to access this resource? You do have a network in between. Okay, so you're going to do remote access. Okay. If resources cannot be moved, Okay, and the process wants to continue to access those resources, you allow it to do so, but you say remote access, no longer local access, not a local printer anymore. So you make sure the printer is networked so it can accept print jobs over a network. You can do that, then there is no problem. You move the process, it will send the print command is going to come over network and it will print. You're done, right? So not really done, but I mean it's kind of done. So whenever you have fixed resources, you need to allow remote access because those resources cannot be moved. Yes, otherwise the process is going to crash if it cannot access the resource. It's not going to function. Okay, so that GR there essentially means establish a global system-wide reference. That simply means the resource has to be networked and is able to be accessed over or a network from another machine. It's no longer a local resource. It's a resource that has is networked and can be accessed from somewhere else. Okay, that's all it means. So the only thing you can really do in this case is really provide remote access. Okay? I'll come back to that last one there. Okay, but that GR essentially says global access. Okay, for this other two, we have a choice. Yeah, what we do. Okay, that's why there are multiple options there. Okay, the choice are if you can move it, go ahead and move it. If you can make a copy, make a second copy. Okay, if you want to provide remote access, provide remote access. All of those choices are still available to us. Okay, process was accessing a file, for example, the process moved. You have a choice. The file will move with it, so it can continue to access the file there. Okay? You can make a copy of the file, which means the file, there's an original copy here, a second copy on the other machine. It can still access the file. Or you don't move the file, you simply say the file stays here, all I/O actually becomes remote. It's a network I/O. Okay? So you basically have the file being accessed over a network using a network file system or a distributed file system. So all of those options are still available to us. Okay, so when you have unattached resources, you can do move or you can do copy or you can do remote access. So all those things are still available to us. Okay? If it's a fastened resource, which means it's an expensive resource, you can move it, but it's expensive, then you have to weigh some trade-offs. Okay? So large database, should I move it or not? You can always provide remote access, okay, accept queries over there for this database over a network, for example. Or if you think that network I/O is expensive and this is a very I/O intensive application, then you say I'm willing to pay the price. It may take me a long time to move it, but after I moved it, all I/O becomes local, and this is an extremely I/O intensive application. So network I/O is going to slow it down tremendously. So I'm going to pay this one-time cost of moving it, and then all I/O becomes faster. Okay? So you have to weigh. There's no right answer. Is there remote access better? Should I pay the price and make a one-time copy and so on? Okay? So you will see that the default choice, if it's fastened resource, is remote access. Okay? But you have a choice, you can move or copy. In this case, the choice doesn't exist. It's a fixed resource, you're not moving it, it's not going anywhere. So you really have to make it access the original resource over a network. Okay? And the last line here basically says by type. This was our loosest binding, because it said, if you remember what I said, here is by type essentially means I don't really care. It's a resource of a certain class. I'm not very finicky about it being exactly the same resource. Here your final option which says rebind, which means find any equivalent other resource and that will do fine. Printer is a good example. There's another printer on that new machine. I don't need to send a network job here. I can simply print to that printer. It doesn't matter to me whether it's a Canon printer or HP printer. I just need to print something. Okay? So I rebind, which means I find something that can replace and provide the same functionality. That's called rebinding. Okay? You're not making a copy. You're not moving it. You're not providing remote access. You find something equivalent that will do the job. Okay? So when you have by type, rebind is always an option. So if you find something that will be equivalent, go ahead and use it. Okay, is that clear? Any question? Yes.
Does remote cloning means that all its resources are remotely accessible?
Okay. Question is, does remote cloning means all the resources are remotely accessible? Remote cloning is just saying make a copy. Okay, clone means make a copy. It doesn't tell you how the resources will be accessed after you made the copy. That simply means here's the process. This is memory address space. Take all of its bits and just make a copy on some other machine. Okay? But if it was accessing a file on disk, you still have to deal with this problem. That's an independent problem. It doesn't actually solve Doesn't get solved because you moved the process. Still have to figure out how the process will continue to run. Okay. Any other questions here? Okay. So there is. I'm going to talk also. I'm going to just mention this. We are out of time. We'll come back to this next time. So here is another issue as to when you migrate the process or even code from one machine to another, what assumptions do you make about the systems which are the sender and the receiver? The default assumption is they are homogeneous machines. They are the same architecture, they run the same OS. So I'm migrating a Windows program to another Windows machine, or a Mac to another Mac, Linux to another Linux, and so on. Okay? But what if the two machines were heterogeneous? Okay? How would that work? Can I take a process that's running on Windows and move it to another process that's running on, let's say, some other operating system, different architecture? Okay? So by default, it won't work if the instruction set is different. Some your binary, it won't even run on the other machine. But in certain restricted cases, it may run. Okay? So for example, if you are trying to do this for Java programs, okay, the underlying platform no longer matters. So long as your JVM, okay, doesn't matter whether the original JVM was running on Linux machines. So long as your JVM there, you can run it on Windows or whatever platform you want. Okay? So if you have some way by which you can abstract away the hardware resources, even you can even do a migration in heterogeneous environments. Okay? Or if it's a shell script, it's a Python script. It doesn't matter whether you have, so long as a Python interpreter installed, you can run a Python script on whatever machine you want. The platform doesn't matter. But if it's compiled C code, that is not going to run on some random other platform because there are binary formats matter. The instruction set matters. So if you're talking about migrating a process that's executing some compiled binary code, that is a lot more complicated or nearly impossible in certain cases. There are some limited cases where you may be able to do something. I'm going to come back to that next time. Also show you some other ways by which you can deal with this kind of complexity. And a couple of slides remaining. Let's stop here today. I will continue this on Friday. For those of you who came late, we do have another makeup class on Friday. I'll put that up there. So same time, this room this Friday. Okay, just to make up for snow holidays. And we'll be sort of caught up. Okay, so I'll stop here today.